Welcome to Computer Systems, Lecture 6. Today we'll be looking at transistors and specifically we'll be looking at nMOS and pMOS transistors and CMOS, the complementary pair of those, and we'll also be looking at logic gates and power consumption, so using those to make logic gates. In the overview of this lecture, we'll be looking at MOSFETs, and just to help you understand what the context of this lecture is, we have already now looked at the conceptual logic gates. So we've looked at how AND gates, NOT gates, OR gates, how all of those gates are defined conceptually, but we've ignored how to make them. We haven't thought about how to use the electronics layer to develop these. We've basically just abstracted that layer and said we have these perfect devices, they do logic checks, and then we've said in order to have them work with one another, we have to define some voltage levels. And now we're going to look at how to make these devices using transistors. So the overview, we're going to do MOSFETs as a generic concept, and then we're going to look at how to make these gates using nMOS and pMOS transistors. We'll then transition from those setups where we use resistors into ones where we use complementary MOS. It's just a pairing of CMOS and nMOS. And then we will look at power consumption of these devices. Right, so MOSFET transistors is really just a switch. Any transistor is a switch, but you get different types of transistors. You get BJT transistors, and then you get FET transistors. You could get JFET transistors and MOSFET transistors. Now, MOSFET transistors are metal oxide semiconductor field effect transistors. The field effect part there really tells you something about how they switch. So these are switches, and the question is, how do they switch? The answer is they switch using a field effect. So BJT transistors are current induced switches, while these are field effect induced transistors, which means that they work on a voltage level. So you can also build everything we're going to say now using BJT transistors, but it's less power efficient. These voltage induced switches, transistors, use a lot less current. So just in terms of the definition of these transistors, you will see there are two types. The one is the nMOS type on that side there, and then the pMOS type. They both have a source and a drain and a gate. And this gate is really the thing that says turn on or turn off. And we're going to work at a very high conceptual level where we're just going to say you either apply a voltage or you don't. So a high or a low voltage to the gate, and then the switch turns on or off depending on which one it is. Now, the nMOS is the one, we'll show it again in the next slide, but the nMOS is the one that turns on when you apply a voltage here, and the pMOS is the one that switches on when you apply a 0 volt at the gate here. And that's where, I don't know if you can see there's a little bubble there at the gate. As I said, these just behave like a voltage controlled switch. That's all they do. So we have a definition here of the threshold voltage, and essentially what that means is that when that threshold is exceeded, the gate turns on or off. And typically this voltage threshold is between 0.3 to 0.7 volts. So as it goes beyond that threshold, the switch turns on if it's an nMOS switch, or turns off if it's an pMOS switch. So let's just look at the way that we're going to interpret these switches. So obviously there's a lot more to it, and you will look at these in electric techniques and maybe other similar modules. But for our purposes, we're just going to use the following definition. So that's all you need to know. So nMOS, as I said, requires a high to activate. It requires a high voltage to activate. pMOS just requires a low voltage to activate. And just to go into a bit more detail, for the nMOS, if you apply a voltage here, then this turns into a conductive path. And that's what we're showing here. If gate is 1, then this is as if it's a short circuit. If gate is 0, it is as if the circuit is broken and no current can flow. So when this voltage is low, no current flows. When this voltage is high, current flows. That is the nMOS, and that is similar to an NPN transistor. Then we have the pMOS MOSFET. Now this pMOS works in exactly the opposite way. We have a little inverter here at the beginning, and this just says turn on when the voltage is low. So when the voltage is high, it's off. just what we're trying to indicate here. When the voltage is high, when gate is high, it's this condition, then the switch is turned off. You can see it's open circuit. And when gate is low, as you can see, then we're working with it being turned on. So these are the two transistors that we will use to define or to make our logic gates. Now, unfortunately, these switches are not perfect. They don't work in a perfect conductive way as a relay would. If you don't know what a relay is, go and Google it. But for a relay, it doesn't matter where in the circuit you put this conduction switch. You just flick it and it turns on, and the input and output are independent. However, for MOSFETs, it's not completely independent, and the voltage that we actually define, I'm just going to flick back here and show you. When we say gate is high, in this condition here, we're really saying gate is high relative to that point there. And for the same for the pMOS, when we say gate is low, it's actually relative to that point there that it must be low. So it's not independent on the thing that's switched. The input is closely coupled to the thing that is switched. So that's why we say MOSFETs aren't perfect. In terms of what they do well, nMOS transistors pass 0 well, and they don't do well at doing ones. You should understand why from the relative explanation. And then pMOS transistors pass 1 well because it's all relative to that one, but they do zeros poorly. So therefore, we've been using a combination of the two to build logic gates, a combination of nMOS and pMOS transistors. And when you throw these things together, we talk about complementary MOSFET technology. So it'll become clearer in a second. This is just an introduction. For the time being, all you need to know is we have nMOS, we have pMOS. nMOS turns on when the input is high, pMOS turns on when the input is low, and then CMOS is a combination of the two, and I'll show you how to build gates using those two. What I have on the screen here is a very simple circuit that builds a NOT gate. So let's just consider the circuit for a second. We have a 5-volt source, and then we have a resistor here, we have an output, and we have a transistor. And this here is an nMOS transistor, which means if we apply a high voltage at this input here, then you will see this will turn into a conductive state. We simplify the circuit slightly, so we don't change it, we just show it differently by showing VDD as the high voltage here, the resistor, the output, the switch, and the ground. It's exactly the same circuit, we just don't draw it as a circle, as a closed path. Obviously VDD is relative to that ground there, which is what the 5 volts supplies. Okay, so let's just analyze the circuit real quick. When there's voltage active on this line, and this turns into a conductive path, then we effectively have the following circuit. We have a resistor, this is 5 volts, and this is our output, and this conduction path is closed. So this is what happens if Vx is equal to 1 or high. Make it 5 volts actually, 5 volts. That means that this point here is touching or is connected, is conducting to ground. It's short-circuited to ground essentially, which means Vx is equal to 0. So if Vx is equal to 5, then Vx is 0. Let's just reconsider this case. If Vx is equal to 0 volts, what happens? Well, if Vx is equal to 0, we still have the 5 volt here. Then we have the resistor, we have our output, and lo and behold, this is broken because we have applied a 0 at the gate. And because that is 0, this whole thing here is open circuit. Because it's open circuit, this resistor performs something that we term pull up. It does a pull up operation. Now this is something that you'll come across often in e-design, in computer systems, everywhere, so be sure that you get this. The effect of that resistor is, in the case where you have this setup, that resistor provides a voltage drop. So current flows through it, it gives a voltage drop across there, and it allows this to be 0 because it's touching 0. On the other side, for the secondary case, if Vx is equal to 0 volt, this is open circuit, so no current flows there. All the current flows here if there's current, but there need not be current. The voltage level at this point is equal to this. The reason is especially that because almost no current flows or zero current flows. There's a very small voltage drop across here or zero voltage drop if there's nothing connected on the output. The effect of this is that VF, beg your pardon, VF is equal to 5 volts, which means we've built a NOT gate. Now the logic symbol that you should recall from the previous lecture is just this. Obviously implied is the 5 volt and the 0 volt, but we don't show that. And this is how you make a NOT gate. Okay, let's go to the next one. So let's try to make a NAND gate now. As I said, we have the resistor performing the pull-up function here, and then we just have 2 of these MOSFETs in series. So just think about this from a bigger perspective real quick. The MOSFET here will turn on if this is high. It'll turn on if this is high, this one will turn on. And the effect of that will be that if both of them are turned on, then this circuit path here short circuits. If this path here short circuits, it connects VF to 0, which really is indicated here. If both the inputs are 1, the output is 0. Now consider the following. If either one of these two does not conduct, in other words, if either of these two or both are equal to 0, then you'll have an open circuit here or an open circuit here. Because you have open circuits here or here, no current can flow there whatsoever. Because no current flows here, the only current that can flow is through here. And if you have a very high input impedance device here or no device there, then no current flows or virtually no current flows. And because that, the voltage drop across the resistor is basically 0. So VR is equal to 0 volts, which means this voltage VF will just be equal to VDD, which is high. So in either of these or any of these conditions, the output is going to be 1. So that's how you build a NAND gate with nMOS transistors. What you can see here is it only takes 2 nMOS transistors and a resistor to build a NAND gate. So you'll recall from the previous lecture I said many circuits are built using NAND gates, and it's because it's really simple to make a NAND gate. It's really cheap. And then you can represent any logic function with just NAND gates. Alright, so this is the symbol that we use. Obviously implied is that you need to provide power to this thing. And when we draw it, we just draw it conceptually like this. If you just think about it for a second, in the practical, you will have a chip. And this chip you'll have to provide 5 volts to, and you'll have to provide ground to. And that's this 5 volts, and that's the ground. And then in between are a few logic chips. And these logic chips will be made up with transistors. Now, this is how you make a NAND gate. Let's just consider how to build an AND gate. Now, obviously, just going back here, this is an AND gate with an inverter. So to make an AND gate, we make a NAND gate, and then we just stick an inverter onto its output. So this will behave like an AND gate, a NAND gate. This will behave like an NOT gate. So the combination of the two just gives you an AND gate. And this is what it looks like. This is the implied circuitry, as I said before. Let's look at how to make a NOR gate. NOR gate is very similar. We have this voltage dropper, this pull-up resistor, VR here. And then we have 2 of these MOSFETs, and the 2 MOSFETs are in parallel. What that means is the current that flows through the resistor has 2 possible paths to flow through. It can either flow through this direction, or it can flow through this direction here. There's 2 paths that it can take. So if either one of the 2 or both is equal to 1, current will flow here. And because current flows through the resistor, there's a voltage drop. Or in other words, because there's a short circuit between here and here, the voltage at VF is just equal to 0. So if either of the two inputs is equal to 1, the output will be low. remember this turns into a short circuit, or that turns into a short circuit, or both of them turn into a short circuit. The other side of it, if both of these are off, so neither of them are conducting, it means we have an open circuit here, we have an open circuit here, and because we have two open circuits, the current that flows through here does not know where to go. It can go nowhere. Only path it should be able to find through is there, but here we have a high impedance because we don't have anything here, or if you have another device here, its input is high impedance. I'm just going to flick back, just don't lose me now. If you look at this device here, the input impedance of this transistor is really high. It's a field effect transistor, meaning it works with voltage, it doesn't work with current, and because it doesn't draw current, there's virtually no current flowing here when this path here is killed. So if no current flows through here, the current that flows through here is minimal because the impedance that this device presents as an input impedance here is virtually infinite. And this is why when this is killed, so there's no flow there, then this point here is high because there's almost no current through the resistor, which means the voltage drop across the resistor is equal to 0. And that's why this output F is equal to 1. So considering what we have on the screen here, on the left-hand side looks exactly the same as what we've just had with the NOR gate. Two inputs, as you can see, two inputs, and then the resistor here that acts as a pull-up in case there's no current flowing, a pull-up resistor. Now what we do is we slap a NOT gate onto the back of it, and as you can see here, this here provides high impedance, so it doesn't really matter that there is a path for the current to flow. That current is virtually 0. So if there's no current flowing here, no current flowing here, this presents a high impedance, so whatever this voltage level is will then be taken by this NOT gate. So this is essentially a NOT gate. It'll be taken by this NOT gate and output here. And that's why, let's just do the logic for this one as well real quick. So if this is 0 and this is 0, then no current flows here, so this turns into an open circuit. This here turns into an open circuit, which means no current flows here, I is equal to 0. So this here is basically equal to VDD. Because this is equal to VDD, then this transistor will turn on, so it turns into a short circuit. Because it's a short circuit, current flows here, and this point is short circuited to ground, so VF is equal to 0. So that brings us to this condition here. Right, that's the first point of our truth table. If you then consider the next point, where this is, let's say this is 0 and this is a 1, then current flows through here. This here is an open circuit, or I should draw it like this, sorry. That's an open circuit, which means because current is flowing here, this is short circuited to ground, and there's a voltage drop across the resistor. So this point here is equal to 0 volts. Because this is 0 volts, this field effect transistor here will be turned off. And because that's turned off, there's no path for the current to flow from here to the bottom. Because there's no current to flow, this voltage drop here is equal to 0, which means VF is equal to 1. So that brings me to that point there. Okay, so you can see you can build up the whole truth table using that. And as you can see, the OR gate is built with a NOR gate with an inverter at the back. Let's look at CMOS now. So just going back real quick on this slide, one of the issues here, you should have realized this, hopefully you did. One of the big issues here is that in the case when this transistor is turned off, so it's not conducting, in that scenario, current is not flowing through here, so that's good. It doesn't use a lot of power. There's almost no power used by this part of the circuit. However, if this transistor is conducting, this turns into a short circuit, and then power is dissipated by this resistor. So there's a voltage drop across here of VDD, and there's a current flowing of VDD over R. So if you were to think about the power is going to be VDD squared divided by R. That's an issue. That means whenever this logic gate is in a state where this transistor is closed, it's short-circuited, it's closed, in that case, we're dissipating power just to keep active. So now we're going to look at a different technology that negates that problem or that overcomes that problem. And that technology is just a combination of pMOS and CMOS. I'm just going to flick back again to show you something. Similar to what we've had with these nMOSs, you may as well have designed pMOS transistors and put them at the top and put the resistors at the bottom. So we've just used resistors at the top and nMOS transistors here. You could have designed these circuits also by using pMOS transistors here and resistors at the bottom. I'll show you in a bit more detail in a second. So what we're going to do now is we're going to develop these circuits that don't use resistors but rather use a complementary pair of nMOS and pMOS transistors. It'll become clear in a second. So what the previous slide here says is basically the CMOS circuits functions by an arrangement of nMOS to pull it low and a resistor to pull it high. And the pMOS circuit uses a resistor to pull it low effectively and a pMOS transistor to pull it high. And now we're going to combine that, but we're going to say rather than do that, let's use an nMOS transistor to pull it low and replace the resistor with a pMOS transistor to pull it high. That's what we're going to do. But if you do that, you obviously have to ensure that these two things don't switch on at the same time. Otherwise, you're going to have a short circuit between VDD and ground, but we'll get through that. So this slide is clearly indicated here with a graphical format. Let's just look at this. This is what we've done up to now. You have some kind of a pull-down network, and that determines the logic operation of the output. That's how it works. This is a small little network of transistors, and just flicking back real quick, this is that, this is that. All right. And then you have a resistor, and the purpose of that resistor is to pull up in case the logic network of transistors does not consume any current. That's its purpose. Now we're going to say, rather than have this resistor do that function, we're going to use a pull-up network of pMOS transistors. And this pull-up network of pMOS transistors, we will drive using exactly the same inputs. All right, so we need to figure out a logic structure at the top that complements the logic structure at the bottom. Hence the name complementary pMOS or complementary MOS transistors. So this is an example of a NOT gate. Just looking at the NOT gate, as you can see, we have VDD yet again. We have the ground, we have the output and the input. Now I'm going to just take you through this. If Vx is equal to 0 volts, that means this transistor here will be off, so it's not conducting. This transistor here, because there's an inverter here, it's a pMOS. This pMOS will be conducting, so that's short-circuited. Because this is short-circuiting and this is open circuit, it means Vf will be equal to VDD. So because Vx is equal to 0 volts, Vf, which in this case was Vf, is equal to 5 volts, which is this condition here. Let's do the other one. So now we say Vx is equal to 1. If Vx is equal to 1, then this here will be off. So it will not be conducting. It will be open circuit. Open or off. That's a bit confusing, but it's true. And this transistor here will be turned on. So that'll be a short circuit. Because this is a short circuit, it's pulling that point down to ground. And because it's pulling that point down to ground, Vf is equal to 1, is equal to 0. Because it's pulling down, Vf is equal to 0. And that is the second condition here. Input equal to 1 leads to F equal to 0. And that's just a NOT gate, as you'll probably acknowledge. So here's the NAND gate. And as you'll recall previously, the NAND gate had these two transistors, and they are in series because they both need to conduct to pull this point to 0. Now just think in your mind, we had the resistor here, but now we want to put a complementary pair of transistors here. This logic says both of them need to conduct to make this point 0. The complementary pair of them is either of these two need to conduct to pull this point high. Both of these need to conduct to pull it low. Either of these two need to conduct to pull it high. So that's why it's a complementary pair. At the bottom we've got the serial connection, the top we've got the parallel connection. These turn on if Vx1 and x2 are both 0. Oh, sorry, yes. If that's 0, that turns on. If this is 0, that turns on. So if either one of them are 0, the output must be high, which is this block of conditions here. The other part of that, and then obviously these must not conduct. The other part of that is if both of these are conducting, then the output must be low, so that's pulling low. And if they are both conducting, then this will be off and that'll be off, which means there's no way for it to pull up. So there's no chance for it, there's no logic opportunity for a short circuit between these VDD and ground through any of these transistors. So this gives you a NAND gate. You can also do a CMOS NAND gate, and again, it's just a NAND gate and a NOT gate that provides that input. And again, the input impedance here is high because it's a field effect transistor, which means there won't be any current or very, very little current flowing in that direction here. This here is the logic for a NOR gate, and as you can see at the bottom, either of these two, either of the bottom two, must be conducting to make this a low. Either this one or this one. The complementary logic pair of that is both of these need to be conducting to pull this up to high. So that's why we have a serial connection here and a parallel connection at the bottom, and they never match. They don't ever clash, as it were. So let's just look at one of the conditions. So let's use this one here. So if Vx1 is equal to 0, Vx2 is equal to 1, what is going to happen? Well, this transistor will be turned on because that is 0. This transistor here will be turned off. So already we can see there's no path towards VDD. So our assumption is immediately this is going to be 0, but let's just check that our circuit works. If Vx1 is equal to 0, this transistor will be off, so that's not conducting. If this is 1, then this is conducting, that's conducting, which means Vf is equal to 0. So that checks out. And the top part is just a complementary logic pair of the bottom part. It pulls up when the other one does not pull down, or it pulls down when the other one does not pull up. This is an OR gate, same story. We're just using a NOR gate, and then onto its back, we're connecting a NOT gate. If both of these circuits turn on at the same time, then you'll have a short circuit and the transistors will both turn on at the same time, and there will be large power consumption until one of the transistors burn out. If both the pull up and the pull down networks are off at the same time, then the output is not connected to either VDD or ground. And then that output is said to be floating. Floating just means it's not connected to anything. We don't know what its value is, and it's probably going to be in that, it's probably going to also be in that forbidden zone, but we don't know. We can prevent these by using the rule of conduction, complements. When the nMOS transistors are in series, the pMOS transistors must be parallel. When the nMOS transistors are in parallel, the pMOS must be in series. And that's the logic check that we apply to it. So now we get to something that's a bit more practical, and in the real world, you will see that we're looking at the 74XX logic. So this is what you're going to use in the practical. We have 7404, for example, ICs that contains the NOT gate, and then we have 7408 that contains AND gates, etc. So it's a whole series that contains lots of different types of logic gates. Now these things were used extensively in the 1970s and the 1980s, but now they're largely obsolete, and the only reason we still have them is just for very simple systems, so when you want to play around, or we want to teach students in practicals. It's actually difficult to get hold of these often just because they're not used by industry anymore. And these are commonly called the 14-pin DIP packages or dual inline packages. Importantly, to understand how to orientate this chip, there's two ways to do this. The first way is to look at a notch. If there's a notch there, that's the top of the chip, which means that pin 1 will be here. If there's no notch, then typically there's a little dot here. So you'll have to look at the data sheet, and that dot denotes pin 1. And this is a common feature for all ICs. The dot usually denotes pin 1. And that'll help you to understand how you need to insert your IC into the breadboard. Now, the pins are numbered. As I said, pin 1 is in the left upper corner over here, and it works its way around all the way here until this pin. You can see here VDD, you connect 5 volt to that pin, and you connect ground to that pin. And many of you will do that the wrong way around, and then the smoke will come out and we will have lost a chip. Please don't do it. So pin 14 will be your VDD and pin 7 will be the ground pin. Let's quickly look at power consumption before we get to the end. Power consumption is how much energy is used per unit time. And it is very important in digital systems that you don't use too much power, both for heat reasons, but then also for battery life, for example, of your phone. You can't use much power. So it's important when you design not just to think about the functionality, but to also think about the performance. And this performance could be performance in terms of how quickly it can do stuff, but also increasingly, especially with things like climate change and the abundance of electronics that we have, and the explosion of the Internet of Things, you want to carefully think of how much power each device uses. Even if it does run from Eskom, we don't have much power in our power utilities either. So your digital system draws both dynamic and static power, meaning power that is there even if nothing changes, and then the power that is required to change state. So the dynamic power is obviously when a 0 goes to a 1, there'll be dynamic power consumed, and to maintain that 1 or to maintain the 0 will require static power. Logic gates and the wires that connect them have all capacitance, and that's really why there's this dynamic power requirement. So when you do a 0 to a 1 change, it's not a perfect scenario where the output and input has no capacitance and no resistance. It always has a little bit, and especially if you work on a breadboard with those tracks so close together, they basically make a capacitor. So when you have a fast transition as a logical change from 0 to 1 or 1 to 0, that capacitance will have to absorb the current and change its voltage, which means that it will consume power as well. Now, if a voltage on a capacitor switches at a frequency of F, the charge that discharges and charges the capacitor at frequency divided by 2 times every second. But only charging draws power from the power supply. The dynamic power consumption is just equal to P dynamic, as you can see on the slide. There's a half, and this C is the capacitance, the equivalent capacitance, which you can't read off a data sheet. That's obviously partially the chip, partially the circuit, so you have to probably measure it, but they do give the capacitance for the chip in the data sheet. That's the capacitance. That is the voltage at which the voltage that you're switching, and this here is the frequency at which that switch occurs. Now, obviously, if you change just once, there's no frequency, it's just a singular switch. But if you have a switch, a voltage level that continuously goes up and down at a specific frequency, then this is the frequency. There's also the idle circuit that also leaks a small amount of current. You'll think back to what I said about the input impedance of the transistors being almost zero, almost infinite. It's not. There's also always a little bit of current that is leaking, and that is called the leakage current, or what is typically termed the quiescent supply current. So any circuit that you have, even if it's static, as soon as you give power to your IC, you will see there's a very little amount of current flowing. And again, in the data sheet, you can go and read and see what the quiescent current of your circuit or your IC is. And then there's also the static power consumption, and static power consumption is if you measure that quiescent current and you multiply it by the voltage, that gives you the static power consumption. Right, so that's really a short lecture, but it's a very important lecture. It's important to understand how this works and where your logic gates come from. It's about understanding the cow behind the milk. You need to understand where this thing is coming from, so that you can use it properly, and so that you can understand concepts like power consumption, so that you can understand concepts like the pin is floating. So when you see a pin at a weird voltage, then you have to ask yourself, what's going on here? And then you can think back, oh, probably the inputs are not connected, so I'm not driving these transistors properly. Right, so that's very important. This is a short but important lecture. And in the next lecture, we'll then be combining some of these logic gates. So we'll be moving up the abstraction level again and combining some of the logic gates to form more complex circuits. So that's it for now. Thanks very much.